Hello guys, this is Y, and today we are going to do a tutorial on how to make an Asteroids game. You know that old game you played on Playboy and some similar game console where there are blocks from the top to the bottom of the screen and you have your spaceship at the bottom of the screen and you have to avoid those asteroids? Yes, that's the game. Recently, I've came across a video on people doing an asteroids game on YouTube, but I see that many people are asking for whether there is a tutorial on how to make one, but there isn't. So I've decided that why don't I go forward and design the circuits for this game and figure out how the principles, how the circuits work in detail. And after 2 days, yes, I'm a rookie on designing these circuits, and it took me a long time to figure out how to make it work correctly. And I actually still don't have a perfect working system of this game because there's one thing that I should add later, which is that during the game over scene, you can't collide with the game over pattern or you'll be judged to be game over again, so the game over scene it plays again. That's the problem, but otherwise it is fine. Alright, first we are going to go through the functionalities and general principle of how this digital logic circuit is going to be. And then other details includes how to design the display matrix, how to do the random sequence generator. Of course, we are not doing the random sequence generator by hand. We are not going to design the details. The function is given in the logisim software, but you are going to manipulate it a bit anyways because you want to make the asteroids more spread out. You don't want them to be together. That doesn't look like an asteroid at all. And then you have to design the game over scene and then the scoreboard, and then how do you control your spaceship, based on what do you judge to be lost, and how do you connect the keyboard input. In logisim, actually there's a special component in which it takes in the input from your keyboard, and we will discuss on how to use that correctly in this application. On the extra part, I will go for some issues I have encountered during designing this circuit, and that is if the display is inverted, either upside down or left and right inverted, and also that the game over scene is not playing continuously, because you know that the game over scene, it is supposed to be playing like if you are going to make the game over scene drop down from the top to the bottom, it's going to take a few cycles for it to be entirely on the screen, right? And if you are starting the game over scene based on a losing condition of the spaceship crashing into an asteroid and you start the scene, what if before the scene ends you hit another asteroid and the cycle is turned off and you are back to the display of the asteroid, so the game over scene is not displayed completely, and that's one thing we have to avoid, right? So when the game over scene is dropping, we should make it so that either if you are crashing the asteroids or not, it's not going to interrupt the game over scene. That's what we are trying to ensure. Alright, so let's go and start off with the first part. Before actually starting on designing this circuit, there's a few things we should realize, and that is the asteroids fall from the top to the bottom, the player can move their spaceship from the left to right and right to left, right? So what you actually want is that if you have a few squares here, if you're currently on this square, you want to be able to move in both directions. If you're in this square, you want to move in this direction. But due to the design, I allow it to move in this direction to here. So you can actually move across boundaries, and you can imagine it like it's a circular, and this is your left, this is your right, and they are connected, so you can move across it, right? And then when the asteroid and the spaceship touches, the game over is announced. So in my design, what I'm going for is a 16 column by 24 rows of displaying the asteroids, and then you have another 3 rows bottom displaying your spaceship. So what's the conditions going to be is I compare the location of your spaceship in this row, and I compare the location of the asteroids. So if they are in fact at the same place, you are judged to be loose because you crash into the asteroid, right? So that's the condition of when you touch, game over is announced. Another thing, we want to manage the whole system on the same clock. What this means is that you want to use one clock source only. You want to use one clock to run a lot of things in this circuit. This circuit is not like any other circuit we have discussed before. This is going to be a complicated one. It's going to be made up from a lot of parts. There are a lot of parts. There are score counting, there are the random sequence generator, there are a game over, there are the keyboard input, and then you have the shift registers storing your spaceship. They all require a clock, and it is quite complicated if you are looking at it as a whole and not breaking it down system by system. You have a lot of circuits in there. We will see that later. And C, the player must be able to move faster than the asteroids. This implies that we have a design that, because when we are moving the spaceship, the movement is only registered after one clock pulse. And the movement of the asteroid is also going to base on the clock pulse. So what we are trying to say that the player is moving faster than the asteroid is that in the clock pulse given, suppose this is the clock pulse, you want the player's clock pulse to be higher and the asteroid's clock pulse to be slower, although you are using the same source. So you can add a few counters, right? You can add a few counters and say this is what you use for the asteroid's clock pulse, and the user's clock pulse is here. We will go into details later on this. Only if the user's input is faster than the asteroids, the game will feel smooth. Otherwise, the asteroids move a row, you'll only be moving by a column, and that feels laggy. Alright. In the period where the game over is displayed, no more asteroids falling. So what this means is that when we are displaying the game over message, we want to avoid the asteroids showing up because they will make a message messy, right? We want to make the message appear as words on the very small screen we have used here. We want to let it display words, right? We want to let it display words. So when we are displaying the words, we don't want asteroids. So what we need is that we need to have two display inputs, switchable, using something to the LED display. We want to have a circuitry to toggle between whether the input is the asteroid or the input is the game over screen, right? So that's something we should design. And the scoreboard will count the score. Every row of the asteroid generated is +1 mark. So it will count from 0000 to the maximum of 9999. You can actually add more by yourself if you want. And the score will be reset once you crash into the asteroids. Alright, the speed of the asteroid is adjustable by changing the clock speed of logisim in the settings. Yes, by changing this, you ultimately also change the clock speed this which the asteroid used. So if you change it to be a faster clock speed, the asteroid will move faster because the entire system just sped up. Alright, let's head over and see the general working parts involved in our circuits. Alright, here we got our imaginary working part. First off, most important, we have our clock here, and then the clock, we are going to slow it down using some counter, and then the slowed pulse will be connected to various parts in the circuit. Also, the fastest clock, the original unaltered clock, it will go to the keyboard output analyzer, which analyze which key you press and make a movement. If you press 1, it moves to the left, and you press 2, it moves to the right. Depends on how you design your circuit. Alright, this will go to a game over scene ROM. See, ROM, it stores the message of what you want to display on the screen. About how the message is stored, we will discuss that in detail later. This ROM, its content never changes. Once you set, it never changes. You just need to let it display its content by using a counter to choose the address. So you want to input your contents in a ascending arrangement, right? Also, because you have a input of a gain over scene, and then you also want an input of random sequence generator to act as the random asteroids falling. So you actually have to choose between either the asteroids or the game over scene. So you need to choose wisely about how long the game over scene should last. When should you cut off this random sequence generator? And so the logic here will be a bit complicated, but we will see that later. And this input choosing is connected to the display input control. This display input control is made up of a total 16 column and 24 rows of D flip-flop. The other 3 rows of showing where the player is using another set of register, is a different thing. What we are using here is only a data flip-flop designed to pass on its content to the first flip-flop by each clock pulse. It's in only one direction because it's only falling downwards, right? But in this, we are not dealing with upwards downwards motion. We are dealing with horizontal motions. And then we are not dealing with one direction only. We are dealing with 2 directions. You want to move left and right. So there's a bit of design different. Right. So we have covered the left part. Let's go on the right part. We have a scoreboard controllers. We have a counter. We have a reset condition. What we are going to do is that we are going to have 4 displays, 4 hex displays to act as the scoreboard, and we are going to have counters attached to them. And this is each of them is counting from 0 to 9, right? This is the thousands, this is the hundreds, this is the tens and ones. So you want a reset condition. Binary to hex, because we are not using a 7-segment display here. If I add any more stuff to my current circuit, it makes the laptop very laggy because I already have tons of components in there. So I'm not going to add a 7-segment and do a binary coded decimal convert to 7-segment. That is going to be overkill, and the overall result is not going to be pretty. It's going to be very messy. So I'm using a hex here, which you input a hex code, and you need binary to hex, which is easy. You can see later binary to hex is a easy conversion. And then you want it to clear the score upon game over condition. So what you actually want is the input choose. It sends a game over condition over to the scoreboard. So you see it's interconnected, right? And then this scoreboard it will give instruction to the scoreboard on how to display the score, on what score is it. So you see there's a connection here. And you want a losing condition circuit. Is this circuit, it compares a given information and see if they are equal. So if they are equal, a losing condition is announced, and it will tell the input to choose this game over scene. Alright, so where does it input come from? Inputs come from the display input control. You want the 24th row, the last row, right? And the 24th row and the user's position here. So you compare them if they are equal. And the user position, memory, and controller. So we want a kind of circular linked shift register. A shift register is a bunch of flip-flops in which they can store information, but they can also pass information in both directions with special circuitries. We'll go over how to build that later. And we want the spaceship to always be in the display panel and not disappear, because in traditional bidirectional shift registers, once your information goes over here where there are no registers, the information is lost. So we want, when it goes over here, it acts like a circle and it goes over here and it's forever in this cycle, so the information is not lost. We want that. And finally, we want a keyboard system. We want a keyboard output. The keyboard output is connected by the fastest clock. It sends information to this user position to tell if the spaceship should move in which direction. And then you have the keyboard input connected to the keyboard output analyzer, in which you type here, and it's going to have its own clock. It's going to have its own clock too, and it outputs the SI code. In logisim, this keyboard, it takes input from your physical keyboard, and whatever key you press, it outputs the SI code of that key to the keyboard output analyzer. So I've actually tested for some laptops. I don't know if it works for desktops. Maybe it's also not working for desktops. If you are going for the direction keys, the up, down, left, and right direction keys, they don't have an SI code value. So if you use those, they will not work. So in my case, I designed it to move left on pressing 1 and move right on pressing 2. And then you have a pause button. This pause button, it pauses the movement of the asteroids and also your spaceship. So what it does is that it actually controls the clock. It actually controls the clock here. So how do you actually do this is that you have clock, right? Originally, you have a clock which is connected to a bunch of flip-flops. But then if you want it to pause or play, you want to be able to adjust it. You want another input here, and they are connected with an AND gate, and then only proceeding to the flip-flops here. So what this AND gate does is that only when the input is high, the signal is able to pass. So when you press the pause button, the input is low and it switches off this AND gate and no signal here. No signal here meaning you are cutting off every single clock for the system in every circuitry. So there's one thing named the pause button, actually is a pause of play. Right. And then the LED display. Why is it called matrix? Because it's made up of columns and rows. So that is about the general working parts included in this circuitry. It is going to be a bit complicated and boring and dry to try to explain them all, but if anyone's interested, then good news. Alright, let's head back to the other presentation. Okay, so we are over the general working principle. Now let's move on to the display matrix. So in this software in logisim, the display matrix you can actually adjust. By default, it is actually like this, where the input is from the bottom. It's called a column input. You control a column with each input, right? And the input is not just 0 or 1. It actually depends on how many columns you have. But let's switch the settings a bit first. You are going to each of the rows, you're going to set it to 1 row, 16 columns. How many columns will be depending on yourself. If you are going to do a 20 columns or a 32 columns, that's going to be your job. If you like it, do it. But just bear in mind that for every column you add, you need one more flip-flop to control the contents, and the system will become larger linearly. Alright, so you set it and you set the input as row mode. You don't want it to be in column mode, you want it to be in row, so that it looks like this. This is the input, this is the 16 columns and 1 rows. So what we are trying to input here isn't just 0 or 1. You see we have a total of 16 columns here. We are trying to input 16 bits of information, 16 bits of zeros and ones. So what we are going to do here is that we are going to introduce a new part, which is called the splitter. It takes in multiple outputs, make it to 1, or it can also take in 1 and split it back to multiple outputs. It depends on the bit size and the number of fan-outs. The number of connections here available here is called number of fan-outs. It depends on how you set them. And in this case, you want 16 combined into one output to connect here. So width here is 16. Data width here is 16, so that they match. Alright. And a total of 27 panels. 24 panels are showing the asteroids, 3 panels showing your location of spaceship. And how do you actually set it up is that you want them to be like this, stacked. These are the inputs. And the display is from the left to right, right? The display panel is here in this direction, but the motion of the asteroids is moving down. So we mentioned before that the shift register, it can pass data, right? So what we are trying to say is that the asteroid occurs here. Next clock pulse is going to move down here. So it's like working principle of a shift register, right? Where you shift from here to here. So you want to make the shift registers in a structure which is going down, and then you want multiple registers also going down, but this is showing the first column, this is showing the second column. Let's move on first, we'll discuss this later. Second row takes the first row information, third takes the second, and so on until the very last row. Yes. Right. about the shift registers. So they are going to be connected in this, like this. So what this is going to say is that the information here will be transported here in the next pulse. So is all of these shift registers. And then each group of these, we are going to have a total of 16 of these connected to a splitter, which is 16 bits here and 16 bits here because we have 16 columns. We have this splitter and grouping them into one and then connecting to the input of the LED. So we have a total of, because if we are using a 16 over 27, no 27, 24, we are going to have 16 times 24, 384 flip-flops used as a part of the shift register. So there's going to be a lot of components, a lot of connections. There's going to be a tiring work if you don't know how to copy and paste correctly. Yes, copy and paste has its own techniques. So you want two types of inputs, as mentioned before, about the asteroids and the game over scene. Alright, for multiple inputs to choose, we use a MUX, or its name is multiplexer. What is it? A MUX takes in multiple inputs but only allow one at a time. Let's say we are having a 2-to-1 MUX. How does it actually work is that, let's say we have the asteroid input here and the game over scene input here. We have a 2, but the output is only 1. You can select here. When this gate is 0, it goes for the first output. When this gate is 1, it goes for the second output, so on. And for if we are dealing with 8-to-1, the select bit is in 3 bits from 000 to 0 to 111. You can see 000 representing input 0, the first input, 111 representing input 7, the 8th input here, the last one here. So that's how a MUX multiplexer works. Originally I wanted to build a MUX using simple logic gates, and I want to try to explain how multiplexer works. But then for every single operation I move, let's say connecting wires, putting down logic gates, at that time in the designing the circuit, every operation is taking like half a second for the computer to figure out if placing there does not contradict other components I have put here, and it's very torturing to do so. So I've just used MUX. And if you want me to do a video on multiplexer, how multiplexer works, I will be glad to make it. Just leave a comment if you want to listen to how multiplexer works. Also, if you want to listen to how a multiple bit data in multiplexer works, you can leave a comment. And we are using only a 2-to-1 multiplexer because we only have 2 inputs to choose from, so we are using something like this. See, something like this. This is from the choosing circuit. This is going to be the splitter. This is going to be the LED display here. So generally, it looks like this. You need a MUX here, multiplexer.